Hi guys, so we're going to talk about just some general vectors things today to kind of get you into understanding what a vector is and different ways to express vectors. So firstly, we need to know the difference between a vector and a scalar. So a scalar is describing something that has magnitude or size only. So it can have units, it cannot have units, and it will not include a direction. So things that are scalar quantities could be things like temperature, distance, speed, mass, just a regular number, area, volume, and many more. Now a vector is a quantity that has both magnitude and direction to it. So something like displacement, velocity, force, weight, these are different things that can be expressed in vector quantities. Acceleration is another one. So anything that also includes a direction as well as size is a vector. Okay, I'm sure some of you have discussed things like this in physics before. So we're going to decide if each of these is a vector or a scalar. So before I say the answers, I just want you to pause the video and I want you to think about whether each of these things would be vector or scalar and why. Okay, so pause the video for a second. All right, so a car traveling at 50 kilometers per hour to the east, so this has magnitude and it also has direction. It is a vector. Okay, a child pulling a wagon with a force of 100 newtons at 30 degrees to the horizontal, so magnitude and direction, we've got a vector. Okay, mass of 88 kilograms. Mass is a scalar quantity. A woman skiing at a speed of 25 kilometers. Again, this doesn't have a direction, so we'd say scalar. A parachutist falling at 20 kilometers per hour. So falling, I think that kind of indicates a bit of a direction, which would be a downward direction if they're falling. So let's say vector for this one. Acceleration due to gravity. This is also a vector quantity because gravity has a direction to it. The number 5, this is just a regular number. This is a scalar. Your weight on a bathroom scale. This is, when we talk about weight, this is a force due to gravity. Okay, so weight and mass are different. Weight is the force due to gravity and therefore has a direction to it. It's a vector, whereas mass is a scalar quantity. Okay, so a couple different ways to represent vectors are in words. So you guys saw some vectors above here represented in words. So a good example of that is 5 kilometers at an angle of 30 degrees to a horizontal. You can express a vector in a diagram. So this is called a geometric vector. This is kind of the title of our unit. So we're going to be expressing vectors in a variety of different ways. So let's express this vector here in terms of this diagram. So what we would have is 30 degrees here, 30 to the horizontal. This is the vector. And then what we would do is typically we would create a scale so that we can create a scale diagram that actually represents this vector. So let's just say in our scenario, 1 centimeter is equivalent to 1 kilometer. And then I would make sure that this vector is 5 centimeters in my diagram. And I would label this as 5 kilometers. Okay, so a lot of times we try to create scale diagrams when we're expressing something as geometric vectors. So my suggestion for this unit would be that you have always a little ruler on hand for when you're making diagrams. It will also be super beneficial for you if you have a protractor that you can measure angles with. And And yeah, that will allow you to create really great scale diagrams. You can also use your scale diagrams to check your mathematical calculations, which is great. Okay, so we can also express vectors in symbols. So there's two ways that we use symbols for vectors. One of them is the tip to tail notation, or basically we label with a starting point and an ending point. So point A would be considered the tail of the vector, so we would call this A, and point B would be considered the tip or the head of the vector, and that will always have an arrow on it indicating the direction that the vector is going in. And we would call this vector AB. So we'll have AB, and then you create a little vector symbol by putting this little arrow above AB. So it means it's a vector. The other way that we can express a vector is when we have a vector, we could just call it a single name, which would be something like V. You can use any letters you want, really, and that could represent a single vector as well. Okay, so one important thing to kind of note here is that anytime you see this notation, this will be the tail of your vector, and the last part here will be the tip or the head of the vector. Okay, either word is fine. Okay, and we talked about magnitude above. Magnitude is going to be the size of the vector. And when we use a notation for magnitude, we use the absolute value brackets. So if I wanted to say magnitude of vector AB, I would draw these absolute value brackets around it. Or if I'm using the single letter notation to represent my vector, I'll draw those absolute values around it. And it basically just means the magnitude of vector AB or the magnitude of vector V. Okay, because vectors, when we're talking about magnitude, we're talking about a length. Your magnitude is always going to be a positive value. Okay. There's a couple ways that we can express the direction of a vector. So I'm going to show you a couple notations here. When we say with respect to the horizontal or from the horizontal, usually we're measuring the angle in a counterclockwise direction starting from a horizontal line. So for instance, this one we would say 14 centimeters at 110 degrees to the horizontal. Okay, and then typically as well, if we're drawing a vector diagram, we would try to make a scale or actually draw this as 14 centimeters. Now 14 centimeters is a little bit long, so you might do something like 2 centimeters to 7 centimeters to show, like, if I did 4 centimeters, then it represents 14 centimeters or whatever. So typically we'd try to create a scale to actually draw this to scale if this is an actual like geometric drawing. Okay, and then 6 meters at 70 degrees to the horizontal. So you're going to start with a little horizontal here. And if you have a compass, you can actually measure this out exactly. And let's say you did something like 2 centimeters is equal to 1 meter. Then we would draw a 3 centimeter line here to represent 6 meters. And we would try to keep it at 70 to the horizontal. So you might have something, that was bad. Might have something like this. Okay, so the length of this would be 3 centimeters, but you label it as 6 meters. And then you would have 70 degrees in here. Okay, the second way that we can indicate the direction of a vector is called true bearing. So it's an angle that's measured from north, always in a clockwise direction. So the description of this direction would basically be we have 2.3 kilometers at a true bearing, or sometimes you won't even see the word true. It might just say at a bearing. Okay, so this word could be like an optional word at a bearing of 135 degrees. So if you don't see this word true, but you just see at a bearing of 135 degrees, you can assume that that's a true bearing. Okay, and then another thing that you're going to see is for angles less than 90 or less than 100, I should say, you'll see a little 0 in front of them. So all angles all the way from 0 to 99 need to have a 0 placeholder in front of them until you hit 100. So if we were to create a diagram here, we'll create the north, east, south, and west lines, and then we're going to measure out about 60 degrees here from the north line. Okay, so maybe something like this. And typically, again, we would try to have a scale here. So maybe in this case, 1 centimeter is equivalent to 1 kilometer. And then we would make this line 2 centimeters long. Okay, so we would see 60 degrees there, and we would label this as 2 kilometers. Okay, and we can also create a name for this vector if we want. Let's just say maybe it's vector W, and we could label it vector W. All right, the last way that you might see directions indicated is quadrant bearing. And quadrant bearing is going to start at either the north or south line, and it's going to go toward the east or west line. So for the first one here, you're basically going to indicate the magnitude. So in this case, it's 9.8 newtons. Okay, you may see the word quadrant, you may not. But if I just see bearing, I'm not going to assume true bearing if I see north and west or south or east or things like that. So that's how I can differentiate between true bearing and quadrant bearing, is that with quadrant bearing, you're going to see north, south, east, west, kind of bordering your angle. Whereas with true bearing, you'll just see the measurement of the angle itself. Okay, so we don't necessarily need to have those words in there, but you can write them if it makes you feel happy. So this one's going to be south, and then we're going 35 degrees to the west. So we would say south, 35 degrees west. All right, so if we want to draw the one below, we'll usually measure, label out our north, south, east, west lines. We would typically come up with a scale. So you could choose a scale here, maybe like you could say 25 centimeters is equivalent to, you'd say 1 centimeter is equivalent to 25 kilometers per hour if you wanted to. And then you can just draw a 1 centimeter long vector. So we would have, it's going to start at north and go toward the west. And this will be 80 degrees here. Okay, and then you would label this as, maybe it's vector W again, and you would label this as 25 kilometers per hour. Okay, and then you can make your line, because you created this scale here, you can make your line 1 centimeter long. All right, so one important thing is being able to kind of switch between the two different notations. So this is going to kind of help us once we get to some of our application questions to be able to see how much is between certain horizontal and vertical lines. So write a true bearing of 150 degrees as a quadrant bearing. So it will be helpful in some of these cases just to draw out a picture. So we're going to start from the north line. We will rotate in a clockwise direction, 150 degrees. So that's going to be approximately here. So if we think about this in terms of north, south, east, west, we will always choose the line that is closest as far as north and south. So in this case, this one's actually closer to the south line, and then we'll go toward east or west. So I know if this is 150, this blue slice, this must be 30 because this is a line that's 180 degrees. So we would say south 30 degrees east. Okay, and then same kind of idea here. So if we're going from quadrant bearing to true bearing, we'll draw out a picture here. This will be 50 degrees here. And then for true bearing, we're always starting from the north line and rotating this way. So a way that we can figure this out is if I know a full rotation is 360, this will be 360 minus 50 to get this remaining blue slice here. So that should be 310 degrees because it needs to equal out a full rotation of 360 there. All right, so there's a couple ways that we can describe vectors, a couple words that we use. So equivalent, parallel, and opposite. So parallel, we're very familiar with this. It means that the vectors can either have the same direction or the exact opposite direction, but they don't necessarily have to have the same magnitude. So one thing that I could say here is that vector AB is parallel. So we use these two parallel lines to vector CD, or I can even say vector AB is parallel to vector DC. So the vector going in the opposite direction from D to C is parallel from the vector going from A to B. Doesn't matter if they're going in the same direction or the opposite direction. Okay, I could also say here BC is parallel to DC, or BC is parallel to CD. Equivalent vectors are vectors that have the same magnitude and the same direction. The location of the vector doesn't necessarily matter, but you can see kind of below, if I took any one of these three vectors and slid it or translated it on top of another vector, it would be exactly the same. So they're all parallel, they're all equal in magnitude, which means that they're equivalent vectors. So the way that I would say that is that vector AB is actually equal to or equivalent to vector CD, and that's also equivalent to vector EF. Okay, I could also say it in reverse. The reverse vector, BA, is equivalent to, not DA, DC. And this is equivalent to FE. So if I say that, I'm essentially just reversing the direction of the vectors here. But if they're vectors all in the direction toward the right are equal, then those same vectors in the direction toward the left are all equal. But normally we just kind of leave it at this because we already can see that the direction of these vectors is toward the right. But yeah, I can definitely write it in that opposite notation as well. Okay, and that brings us to opposite vectors. Opposite vectors have the same magnitude, but opposite directions. So we could say with these two vectors over to the right here, that vector AB is equal in magnitude to vector BA, but we can't say AB is equal to BA because these point in opposite directions. So there's a couple ways that we can write expressions for opposite vectors, and that's by placing the negative sign in front of the vector or reversing the order of the letters when we write it. So the opposite of vector AB can be written as negative AB, which is AB but in the reverse direction, or you can write it as BA. So One thing that we might be able to say with these two vectors is that vector AB equals vector BA, but in the opposite direction. So we would put a negative in front of it. Okay, or we can write it in the other way, which would be to say negative AB is equal or equivalent to BA. So we're just saying if you took AB and switched its direction, these two vectors would be equivalent. Okay, so we're given a vector here, AB, and we're asked to draw an equivalent vector, CD, and an opposite vector, GH, and write the equations to show the relationships. So with a ruler here, as best you can, you're going to create a vector that is parallel and equal in length to AB. I didn't do an amazing job, but you guys kind of get the idea there. Okay, so this is vector CD. Notice it goes in the same direction, it's equal in magnitude, it's parallel. So for this one, I can say AB is equal to CD. Okay, for the opposite vector, we want to draw something that's still equal in magnitude and still parallel, but it goes in the opposite direction. So we're going to label this GH. And what we would say is that AB is equal to GH, but in the opposite direction. So we would want to switch its direction by putting a negative in front of it. Or another way that you can say this is AB is equal to HG. Okay, but normally we would defer to this method to show that they're opposite vectors.